Okay, so question 7, we're going to have a question about electromagnetic induction. So we've got a basic generator, and we can see they're going to move a magnet into the coil, then they're going to move the magnet out of the coil. So in it goes, then it'll be stationary for a bit and it'll go out. So we're expecting either the needle's going to go backwards, no movement, and then forwards, or it's going to go forwards, no movement, backwards. So we're after that. So can't be A, can't be B. C looks good because we've got this idea of an alternating current. We can see it goes forwards when we push it in, it goes backwards when we push it out. It's going to have to be C. Done. Give 2 ways of increasing the deflections on the milliammeter shown. So what can we do? Well, we can increase the coils. We could use a stronger magnet, or I could wiggle it in faster. Remember, the process of moving it faster in and out doesn't just increase the voltage. So imagine that's it with the slow. Remember, it also increases the frequency. So if I just draw that over the top. So yes, it'll give a bigger voltage, but we'll also have an increased frequency. So move the magnet faster, use a stronger magnet, increase the number of coils. Note, do not increase the length of the wire. Because if I was to increase the length of the wire over here, well, if it's not experiencing a change in magnetic field, that we're not going to increase the deflection. Okay, so this one is loudspeaker. I've got to teach this to you at some point. So what we can see now is we've got an alternating current in. And then this is going to induce a changing magnetic field in that coil, or the solenoid. That's then going to interact with the surrounding magnetic field, and this will produce a force according to the motor effect. Because we've got an alternating current where it goes one direction then the other, this is then going to make the solenoid move, this coil. This coil is attached to a big paper cone, so that's then going to set up compressions and rarefactions in the air. It's going to vibrate and push air. So let's tidy that up in terms of kind of like a memory method first. So first job, talk about the alternating current in. Next part, this induces a changing magnetic field in the solenoid. Next part, this interacts with the uniform magnetic field. This produces a force, let's just change that to an F, according to the motor effect. The solenoid will now move in and out. It is attached to the paper cone, which is then going to vibrate air, setting up compressions and rarefactions. So that's our model. So alternating current in induces a changing magnetic field in the solenoid. This interacts with the surrounding uniform magnetic field. This creates a force according to the motor effect, and then the solenoid vibrates, which makes the paper cone vibrate, which makes air particles move. So alternating current is inputted into the coil. You can see I'm just going to tick off that. Done. This induces a changing magnetic field in the coil, or the solenoid, which is just a coil of wire. The changing magnetic field in the coil interacts with the surrounding uniform magnetic field to produce a force using the motor effect. This causes the coil to vibrate at the same frequency as the alternating current. This causes the paper cone to vibrate air particles, creating a longitudinal sound wave with compressions and rarefactions. There you go, that's your model answer. So if I just get rid of all of that, because this is something that I've got to teach. I haven't got many lessons left to teach, to be fair. So if I just quickly go back through that, we can see it's alternating current in. This induces a changing magnetic field in the coil. This interacts with the uniform magnetic field. This creates a force according to the motor effect. Because it's an alternating current, this causes a vibration in the coil, or a force in the forwards and backwards motion in the coil. This makes the paper cone vibrate, which pushes air. And there you go. That's that model answer gone through. Okay, lovely. Thank you. Oh, I better check that is the end. No. So figure 18 shows a transformer, and we can see what have we got going in. First part, we're going to check which way the voltage is going in, and it's going in this way. I can see I've got more coils on the secondary coil, so this is a step-up transformer. So state the purpose of the transformer. It's a step-up transformer. It will increase the voltage. You could get the mark by saying it'll decrease the current. And we've said, remember, if it was 100% efficient, the power on each side equals each other. It then says, calculate the output voltage of the secondary coil. Use an equation from the list. So we've got NP over NS equals VP over VS. That's the one that you're going to pick. Substitute the values in. So 18 over 26 equals 230 over X. So we can then rearrange that. So divide both sides by 230 and we're left with 1 over X. And then if we wanted to, we could take the inverse of that. Or what we could do is if we're left with a value like this, there you go, so 1 over X equals that value. Or we could just do, so that I don't get 1 over X, I can flip both of those over. And now it's whatever you want to use in terms of your maths. So I can find the value for 1 over X and do the inverse function. So literally go like that. Or I can just flip these two over. Either way, it's going to give me an answer, 332.2. And you just pick whichever mathematical method you're happy with.